Well, hello, ladies and gentlemen. Mr. Dorfler here with another video in Intro to Chem Phys. Today we are looking at section 15.2. Also want to welcome in Mr. Hampton's classes as well. Anyway, what this section is going to cover are some of the things that we just touched base on in the first section. We're going to talk about amplitude, frequency, period, doing one of our really only math questions that we're going to see, or we might see a couple in the next section, but not as much as we've been seeing thus far. And so you're going to need your notes out, your calculator, and I think that's it. Now, originally I thought I decided to do half the section today and then half Monday. But after some deliberation and thinking, I decided I think I'm just going to go ahead and do the entire section today, okay? Now, with that being said, I might go a little quicker in terms of the content in here, meaning I won't spend as much time on slides. Once I've gone through the material and kind of expanded on where I can expand on, I'm going to go ahead. You can always at home pause the video to finish your notes on that slide before going on to the next slide, okay? So keep that in mind. So anyway, let's start 15.2. Once you're ready, here we go. Wave properties are the focus of this topic, and we're going to be looking at first amplitude. Now, we talked about amplitude in the first section. It's the maximum distance that the particles of a wave's medium vibrate from their rest position. If I get my fancy little pointer here, again, this little dotted line will be its rest position, meaning if there were no disturbance and no energy flowing in this medium, particles would be just sitting along this line. But as a wave of energy goes through this medium, the particles vibrate up and down all around that rest position. Transverse waves all have very similar shapes. Okay, this is a transverse waves. It does not matter how big they are or what medium they travel through. Transverse waves are all the similar shape. Now, do you remember what transverse waves particles do? Okay, or describe that. We talked about it in the first section. As the wave is moving horizontally, the particles move perpendicularly. Okay, they don't necessarily move in the direction that the wave is traveling. One type of transverse waves is what's called a sine wave. And this is an ideal sine wave, and it has the shape of an S on its side, as we see here. These all look like S's on its sides. Many transverse waves are not, in fact, perfect sine waves, but their shapes can be approximated by the graph of the sine curve, which is higher math we don't need to worry about right now, okay? Anyway, anyway, the greater the amplitude, the greater the energy that it transfers, okay? So we'll tend to see greater distances, meaning greater amounts of energy. All right, next thing we talked about in the first section also is wavelength. It's the distance from any point on a wave to the identical point on its next wave, or the neighbor's wave, okay? It is the distance between two successive identical parts of a wave, and it's used, or it's symbolized by the Greek symbol lambda, which is right here. Okay. Transverse waves, their wavelength is the distance from one crest to the next crest, from one trough to the next trough. Or if we even pick this point right here, if you find my little pointer on here, if we pick this point and that point, which is identical to location from this point, except on the neighboring wave here, we can measure the wavelength there. Any point along this wave and the identical point on its next wave, we can measure the wavelength. Longitudinal waves, it's the distance between two compressions or two rarefactions. Now, longitudinal waves are when we describe the spring, when we compress or elongate or stretch out the spring. And so when we have areas of compression, we can measure between that and another area of compression, or we can look at areas of rarefactions. So two areas that are stretched out, we can measure the distance between those and measure our wavelength in a longitudinal wave. Now, the shorter the wavelength, the more energy it carries. So basically, if we look at a transverse wave, meaning the tighter these little amplitudes are, so the shorter the distance between 2 points, the greater the energy. All right. Many wavelengths are difficult to determine because of their complicated shape, like sound waves. Okay, now we start getting into the math area, okay? We're going to be looking at how we relate period and frequency together, and also wavelength over the next few slides. Anyway, we mentioned what a period is in terms of sound waves. It's the time that it takes for a complete cycle or wave oscillation to occur. It's the time between two successive wave crests, or we also say it's the time required for one full wavelength to pass a certain point. It's key to always have a reference point when we're trying to measure the period, how long it takes for the full wave cycle to pass, okay? It is represented by the symbol capital T, and it uses the unit of seconds. Now, if I move my pretty face here and look at how we can measure a period, if we have a tuber sitting here and he is currently our reference point, okay, so he's at the top of a crest. We start the timer at that point once he reaches that crest of that wave and time how long it takes him to go back to the identical location on the next wave. So as you see here, this arrow is representing the wave that we're going to end our timing. So we start, and as the waves start to pass, that tuber now goes into the trough after 1 second, and then finally gets back to the top of the crest after 2 seconds. So the period for this scenario would be 2 seconds. And I'm going to try to move the face down here. Okay. Then we talk about frequency. Okay. All right. So frequency is the number of cycles or vibrations per unit of time. Now, the number of waves produced in a given amount of time, it's whatever you want to say, but that's what frequency is. And it's represented by what I call a fancy F, okay? Like a fancy lowercase f. We label it in the unit of hertz, spelled H-E-R-T-Z, like we see here. And the abbreviated version of hertz is capital H-Z. It is the SI unit for frequency. And so what it is, it's one vibration per second. So oftentimes when you hear us talk about hertz, we also say like 20,000 vibrations per second, as we see down here in this example here. So we could typically see frequencies between 20 hertz, which is very low, and 20,000 hertz, which is very high. Not everybody has that range. Some can have a slightly greater range. Some can have a much greater diminished range than that. But either way, this represents 20 hertz or 20 cycles per second, and 20,000 hertz or 20,000 cycles per second. So how do we relate frequency and period? Well, the frequency is simply the inverse of the period. And so we get this quote-unquote formula where frequency is 1 over whatever the period is. So if we look back at the previous example with the tuber and the waves, we saw that the period was 2 seconds. So if we take that and determine the frequency of those waves, again, we take 1 over that 2 seconds. Okay, again, this is from a few slides ago. And so we get 1 divided by 2 seconds, and we get 0.5 hertz, or half of a cycle per second. And that's how we do it, okay? Now, another thing, another part of wave properties is wave speed. So now we have another formula that we're going to use, and that is called the wave speed formula. The speed of a wave is equal to the wavelength divided by the period, or the frequency multiplied by wavelength. It all depends on how you set it up. If you know the period, then you do the wavelength divided by the period. If you know the frequency, then you know you take the frequency and multiply it by the wavelength, okay? So I'm going to write both of those down here in just a second. Anyway, this tells us how fast a wave moves and how far the wave travels in a certain amount of time. And so one of the formulas that we're going to work with today is V, or the wave speed measured in meters per second. So that gives you an idea of what units we have to be in, is equal to frequency in hertz and wavelength in meters. So wavelength must be in meters. So write down the wave speed formula, determine the knowns and unknowns, place the known values and unknowns into the formula, and calculate. We've kind of shortened up the steps to calculating this. Another version of this is, as I'm going to write down, again, we could have the speed is equal to the wavelength divided by period. Okay? That's the best I can write with my mouse, ladies and gentlemen. So the wave speed is equal to wavelength divided by period. That is the second formula that we could use if needed, depending on what we are given in the problem. Okay, so make sure you write that down. So we have a practice problem that we're going to do next. All right, so we're looking at a string of a piano. It produces a note called the middle C that vibrates with a frequency of 262 hertz. If the sound waves produced by this string have a wavelength in air of 1.3 meters, what is the wave speed of this sound wave? All right, so again, write down what you know, write down what we're solving for. Okay, so what we know is that we have, where's my camera? Okay, we've got frequency of 262 hertz. I'm just double checking. And a wavelength of 1.30 meters. So what we're trying to find is wave speed. And so we go ahead and write our wave speed equation. Frequency, since we have frequency, we're doing frequency times wavelength. And so we just go ahead and plug in our values. 262 hertz times 1.3 meters. Now I'm also going to write it what we could do it so we can get our proper units. Remember, hertz is per second, or cycles per second. So really what this means is we have 262 cycles per 1 second. And so by doing it that way, in fact, you don't even have to write cycles if you don't want to. I'm just kind of giving you a visual. 1.3 meters. Now again, this is the same equation. I'm showing you how to write it both ways. And by setting it up this way, taking the hertz out of it and just putting it in its mathematical form of 262 quote-unquote cycles over 1 second, that allows us to get our unit of meters per second, or meters over second, which is what we need to have for our wave speed, okay? And so once we have our values written there, you go ahead and calculate 262 times 1.3, and we get 340.6 meters per second. And that is it. Now again, pay attention to what the problems are asking, because if you are given the period, then you have to do wavelength divided by t. Okay? So make sure you read it carefully. All right. Back at it now. We're going to go back into our notes, and we're going to finish off with the next handful of slides or so. All right. So, differences in wave speed. Let me make sure my camera's fixed here. So wave speed is going to depend on the medium through which the wave travels, okay? Sound waves, I should say, travels 3 to 4 times faster. Sorry, I got distracted. Sound waves travel at 340 meters per second in air. But in water, sound waves travel 3 to 4 times faster than in air, okay? And there's a reason for that we might get into in a little bit. So the speed of a wave is constant in a given medium. So wave speed does not depend on the frequency of the wave. Example, creating waves on the rope that we talked about in class. No matter how fast you shake your hand up and down to create waves on a rope, the waves will always travel at the same speed. Shaking your hand faster just increases the frequency and decreases the wavelength. So again, doesn't matter how fast you shake that rope, how big you do your amplitudes on the rope, it's always going to be a constant speed in that same medium. So, wave speed and kinetic molecular theory. Here's where we get really scientific with you, and this is what explains why sound will travel faster in water than it will in air. So, the wave speed will be determined by the state of matter of the medium through which it travels. So, it can travel through each state, a solid, liquid, or gas. And each state of matter has a different degree of organization at the particle level. Let's look at gases. Gases, we have the molecules that are far apart, okay, like what we see right here. Molecules on gas must travel a greater distance before bumping into another molecule, and waves travel the slowest through a medium in the gas state of matter. We even start to see in winter times, which you can start thinking about now when we start getting into cooler temperatures, that with the air being cold, the gas particles are also going to be quote unquote cold, meaning they're going to move slower, okay? And so you're going to see that typically in wintertime, sound doesn't travel as far than it does in the summertime because there's so little energy already out there in the molecules that they don't tend to propagate as far. Liquids, where we have molecules that are much closer than they are in gases. So if we look right here where my pointer is on the right-hand side, and they are free to slide past one another. The vibrations of the waves are transferred easily from one molecule to another. They will travel faster in liquids than they do in gases. And then finally, we have solids, okay? Here in solids, the molecules are closest together and bonded tightly to each other. The vibrations of waves are transferred from one molecule to another because once one molecule of solid begins to vibrate, the other molecules of solid almost immediately begin to vibrate. And so waves actually travel fastest through solids. Okay? It's all because of how close their molecules and particles are to one another. All right. Moving on to the next. Again, excuse me. Anytime you feel that you need to pause the video to write your notes down, do so. I'm just trying to make this video as short as I can so you're not sitting here for an extended period of time, okay? Now, we mentioned that light itself was also a wave. And so we can talk about the speed of light and the speed of light through mediums. In empty space, the electromagnetic waves travel at the same speed. No matter what type of electromagnetic wave they are, in space, which is a vacuum, they will travel at the same speed. And we basically say that this is going to be known as the speed of light, which has a value of 3.00 times 10 to the 8th meters per second. Think about that. 3 times 10 to the 8th meters, light will travel every second. That's a big distance here. That's why it only takes approximately 8 minutes or so for the light from the sun to reach Earth. Visible light, we have a very small window of light frequencies that we can actually see. And what visible light is human eyes can detect. The visible light spectrum frequencies range from about 4.3 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz. So not a big window, okay, compared to everything else that's considered an electromagnetic wave. Now, the different colors that we see, that's all based off of the different frequency of light. So red has a different frequency than green, green has a different frequency than blue, so on and so forth. That's, the colors that we see are the colors of the rainbow. I was trying to say Roy G. Biv at the same time. I'm getting excited here. So, when we talk about electromagnetic spectrum, it's the full range of light at all frequencies and wavelengths. So, since the speed of light is constant, frequency can be calculated using this equation, where C, the letter C is represented as the speed of light, as we saw up here, is equal to the frequency times lambda, if the wavelength is known. And wavelength can also be calculated using C equals frequency times lambda if the frequency is known. So if we're trying to find frequency and we know what wavelength is, we could rearrange this equation to help us solve for what we don't know. Because c is always constant. It is the speed of light. So this c will always have a value of this in our calculations. Okay? So we just have to worry about rearranging this equation. Again, this is the same equation here for these two. Just rearrange it to solve for whatever we don't know and using what we do know to help solve for it. One of the last things we're going to talk about is known as the Doppler Effect. And this is motion between the source of waves and the observer is going to create a change in observed frequency. For sound waves, this motion creates a change in pitch. This is known as a Doppler effect. I'm sure you've all heard this. If you've ever heard the sirens of an emergency vehicle as they approach you and as they pass you, or if you heard somebody's loud radio as it approaches you and goes past you, notice that there's a pitch change with that sound. I'm going to give you an example here on the next slide. And it all depends on your point of view, which that video does. It's a real quick video, like 8 seconds, but it does a great job at showing you how your viewpoint plays a key role in the whole Doppler effect phenomena. Doppler effect, as we said, is an observed change in frequency of a wave when the source or observer is moving. It occurs in light, sound, and other types of waves. And we use Doppler effect to track storms. That's why you call it checking the weather. Men and women say, let's check the Doppler radar here. That's what they're doing. They're checking the distance, really, but in the motion of the storms in comparison to where the radar is. And so they constantly feed back to that Doppler radar, which if I move here, okay, this would be an example of a Doppler radar where it's, kind of a 360-degree ball that can go in all directions. That's why you see that big white line, almost looks like a radar in an airport as it goes, and it highlights and it produces these readouts like you see up here where my little pointer is here. So the rain, the snow, the hail, whatever, anything, if there's a tornado, it could be debris, okay? The frequency shifts that they get back in from the radar bouncing back to this dome gives us I'm having issues here. Okay, for some reason it does that. Okay, come on, exit out. And so I mentioned earlier in the slide that is a change in pitch. And pitch is determined by the frequency at which sound waves strike the eardrum in your ear. It's still doing that. Come on. That bottom line keeps messing up here. Okay. Higher pitches. Sorry. All this work for this last line here. Higher pitches caused by a sound wave that has higher frequencies. So the higher the frequency, the higher the pitch. And lastly, some examples. Again, a siren moving in an ambulance. As the ambulance is moving towards you, here's what's happening when we hear those weird sounds. Sound waves from the siren as it's moving towards you are being compressed in the direction of the motion. So as it's nearing you, these rings that we see up here are actually, I'm actually going to move up here. So if this is you on the side of the road and this ambulance is going towards you, the sound wave rings, they are compressed. So they are closer together. And so that's why it's going to sound like it's a higher pitch. Okay. The distance between the wave fronts are being shortened, but the wave speed is still going to remain constant. And we perceive the wave pitch to be higher as we have the ambulance approaching us. Because the frequency is going to be much greater, therefore we have higher pitch. But as the ambulance moves away from you, okay, we start to see that the sound waves are expanded in the direction of motion, which is away from us if we're observer A. So the distances between the wave fronts, these blue rings, are going to increase. Therefore, we perceive the siren to be lower than what we initially did. It's all because of the compression of waves and the lengthening of waves as the ambulance moves in conjunction with your observation. So this is the short example that you might hear of a car horn. And so the first half of this video or so is imagine yourself being in the car and honking your horn and traveling. Okay, there's really not, you're going to notice that there's not going to be much of a pitch change at all because you and your position relative to the air horn or the car horn are the same. However, then in the second half of the video, you're going to show that what it sounds like when cars are moving past you and they are honking at you. Let's play that again out and a little louder. There you have it. So that's Doppler effect. So if you ever want to know what that was or that you heard why pitches were different, even though it's from the same thing, that's what it's causing it. Okay. All right. So that brings us to the end of section 2. Again, sorry, last minute change on doing all of them, but I figured this was probably the best case for what we have schedule-wise for next week. So in addition to this video, I'm also, like myself, I'm going to be sending out, well, just check out the instructions in my post for my classes. Mr. Hampton might have something a little different, but make sure you read it. Have a good day, everybody. Enjoy your weekend. We'll be talking to you later. And I'm going to sign off now if I can find my button here. Have a good day.